Thank you
Wow.
so much. I will call her right back and tell her. Thank you so much.
How lucky you are.
Okay, bye.
Not dead, not hurt, not lost.
Nope,
I know
at the
just how
police
great you
station.
feel.
At the police
In
station.
jail, busted.
Yep,
That's okay.
that's good. He's fine.
Well, our security police don't have enough to do, so I think
Yeah.
they were just delighted.
And he's friendly too. Pick up the phone. Pick up the phone.
The person you have called
Sorry.
It's okay, we're just you and me. We can handle this. I owe you already so much.
Hey Mom, law enforcement has him.
Oh, they have him?
Yeah, they picked him
She's
up
so
already.
happy I could hear the doors.
So they found, they're like, is it an Alaskan Malamute Husky thing? And I was like, exactly, that's our boy. So she has him.
Husky.
He's at, yeah, he's at the law enforcement desk.
No wonder they picked him up. What a gorgeous dog.
Okay. I love you, Mom. I don't know. He probably ran by the police station. You know, they saw him driving around, and they just picked him up. He's so friendly. Okay, I love you. I'm sorry. I'm glad they found him. Okay, well we'll have to fix that later. Okay, I love you so much. Bye.
I guess it was you that let the dog loose.
No, there's a hole in the fence.
A hole in it.
She didn't know about it.
Oh, your mom didn't know about it?
Yeah.
Hmm.
So.
So she was feeling guilty and responsible and fearing the worst.
Yeah, cause you know the tank farm by the commissary, that big. My mom works there, so she lets him run around the tank farm because he's a runner, and he has to run like 6 miles a day.
It's a good idea.
So she takes him to work and lets him run around and throws the ball. And he ran away from her and got through a fence in the hole that she didn't know about.
Talk to Melissa Bellarmine. She runs 40 miles a day and she likes dogs for company.
Really?
Yes. She ran a Great Dane 40 miles and the dog wanted more.
Yeah. Yeah, so that's what my mom does.
Runs into it.
And yeah, so whenever there's a runner that runs by, he runs with the runner. And then if they try to pet him, he starts barking. But he got through a hole. And when he's not with my mom, he's like the friendliest little kite in the world. So
Protected, yeah.
they just probably just like, oh hey,
Sounds gorgeous. Black and white. Yeah, I can picture it.
I have a picture.
Let's see how good my picture is.
Oh, this is a good picture.
Yes, just what I thought.
Mm-hmm.
Pick it up to the camera. Let the camera pick it up.
Puppy.
Good story.
So, and he's new too.
Oh, how new?
In January.
Wow, he's adapted to you guys fast.
I see that he's had like 4 previous owners.
So he's used to transitions.
Yeah, and
He looks like about 3 years old there, or less.
he's one.
One.
Like
under 3.
maybe 1.5 years. So then they got him from the original owner got him from Hungary, and like he's been PCS all over.
He came over from Hungary? Did they put him to sleep? Did he sleep through that flight?
I have no idea. Well, he was hungry, and then he came to Europe, and then he was in Europe, and then he came here.
A well-traveled dog.
He has his own passport. It's ridiculous.
His own passport.
That's what they do in Europe.
Passport.
They get like dog passports.
Oh my God.
Yeah,
I wonder if he's on the no-fly list.
it's crazy.
It is. It's absolutely crazy.
I can't believe the cops have him. And then
I can.
that's not the first dog that's in
They've got
heaven.
nothing to do. They sit around all day. They look for little girls riding bicycles without helmets. That's a big bust.
I'm just gonna kill him. It's so funny. Not kill him, but
Kill a dog? Dog didn't know he did anything wrong.
I know. It's just so, she gets so mad when she's worried. It's so cute. So, she doesn't have the operator's number because they changed it. So it's all good.
My dog chased a cat once, tried to break its back, because another dog was talking it into it, just being a dog. And the cat's owner got so worried that he picked up a stick, and I tried to teach my dog not to do that. And the dog loved me so much, he just lay down on the ground, looked at me, says, "Beat me if you want to, I'm yours."
I just texted her. Got a message from someone. Security forces. See, they found, and he wears a reflector, too. My mom has like an own doggy reflector, so he wears one, so he's like really.
I think that's not a good photo of him, he looks squashed up in the nose.
He wears a reflector. So, there's these two girls, they saw him walking around, and she's like, "Can I pet him?" There was like, they're maybe 6 and 5, and they were like, "Oh, can I pet him?" And the older sister's like, "No, he's working. See, he has a vest, he's working." And mom's like, "That's fine. As long as
That works.
That works. They're like, as long as people don't pet him and
Yeah.
So my other dog has a reflector vest too, for when we go walking at night. My mom's.
Are these outdoor dogs?
It's too hot in the house for him. But my
Yeah.
other dog, she's like she looks like a mastiff. So, but she can have it inside because she's getting older, so it's too cold outside for her.
So you don't mind dogs inside? It's okay for you? Drool and fur and dogs are all the way.
Yeah, we have 2 dogs and 4 cats.
Here we go.
Hello, hello.
Hello, hello. Good to see you, Mr. Last Week.
Yes. I gotta say, I'm eternally grateful that you're doing this. Because, I mean, the videos help and everything, but I'm one that I like to see hands-on.
One more time. I'm eternal.
Oh,
I'm
I'm eternally grateful that you're doing this.
Got it. I like you.
So,
You're risking me breaking your camera taking my picture.
Camera loves it. No, I saw the handwriting on the wall that this needed to be done. So we do what needs to be done.
So no 14. I didn't do it yet.
Oh, and the online site seems to be having some issues because I could log in sometimes yesterday, but last night it was down for maintenance again.
I'll take that into account when I look at your
Yeah,
required logins. Definitely will
Yeah.
take that into
but,
account.
my husband helped me issue a trouble ticket back to them. And so they got back to me, they said, "Yeah, we know there's been some outages and that, but make sure you're eliminating your cache." It's like, that's not the
Eliminating your
issue.
cache. God, you're not supposed to do that.
Yeah,
Not true.
but it's like, it's not the issue, people.
No, they've
Because I
given
can
me
get
some
in sometimes and I
comfortable
can't get
advice too,
others.
yeah. Yeah, they said to do some ridiculous things too. I agree with that.
But the one thing that, because the book, you know, we could save to our desktop, I'm hoping that I actually do look every day, but when I'm working in the book, sometimes because I'm working in the book, I don't think about it, it's like, well, I don't need to go to the,
You
so.
do, because I'm gonna delete some pages that you just read and didn't have to read. That's what's
Oh.
gonna happen.
See, yeah, I was looking at that, I'm going, I already read those pages, did I read them in error last, oh, let's read them again, why not, refresh.
That's right, refresh, better understanding. This stuff takes at least 2 readings.
So no 14,
Yeah,
no 72,
three,
so 73,
no,
no
81,
81, and no.
82.
Okay,
That's the 3 that they took out for it.
okay.
Oh, was 14 in it? Oh, 14 from Lane?
Right.
I'm really happy I didn't do 14. I think we're gonna.
You can do it, but you need a formula that's not in the assigned reading pages, so only Karen found it.
Now that I remember, Lane is too hard for me. I I read it and everything, and I understand when I'm reading, but then when I go to the questions, because they don't really go through all the examples,
he's-
I can't equate.
You see, Elaine writes qualitatively, but he tests quantitatively, which
Yeah.
is a bad mix. Bilakowski, she writes quantitatively also,
Right,
so you see examples in how to
right,
do.
so, I'm actually kinda hoping that you'll go over like a couple of the ones from Lane, so I can see what they're actually asking,
Yeah,
because that's where
I
I'm
will,
getting
I will do that by
confused.
special request.
Yeah,
It's good to know what the problem is asking for.
but watching the videos, that also sometimes helps. Like last night when I couldn't get into university, so, and I had printed out what the homework was, and I'd left it in my purse, but I walk to and from the house, and so I leave my purse in the car, and Ron comes home at 10 o'clock at night. So this didn't do me good. So I thought, okay, so then I just started watching, videos, from like Khan Academy and stuff.
Yes, yes,
And
yes.
things were making sense.
They are, he's a good dude, kind of guy.
Yeah.
People like him. Yeah, I'm going to, make sure that it's unlikely this course will ever be taught hybrid again. It just doesn't work, it needs a lecture.
Yeah, yeah. Because I think a lot of people, learn better by seeing math. I was gonna shoot our star student over here and he must, show me how you do one in Lane.
You could've. I don't mind getting emails, I like them.
Yeah, well, I couldn't get into the site last night, so that's what saved you.
Well, that's what you wanna do, also lean on your other classmates.
Yeah,
That's
I had-
encouraging, Leo.
I had someone in the States log onto my account, take a picture of the work and send me all the links and email them
They
back to
hacked
me.
in?
Oh, I gave them my password and
Oh,
everything.
okay.
So I was like, hey, log into my school site, 'cause it's not working for me. So they logged in on their computer in the
Mm.
States and then took a picture of all the homework and sent me the links and emails.
Way to go.
I was like,
Almost as good as doing your own homework.
Hi, sir.
they
Hello.
even helped me save the
My
best
God,
school.
up from the dead, risen and floating in the sky. Oh,
It's called back this
3 weeks later, and you're
Yeah.
out of the tomb. Nice going, and you're walking on 2 feet.
Still
This
standing
is
up.
Nux, in case you don't know Nux, and he's been deployed fixing airplanes in Okinawa, last I heard.
Yeah.
And, he promised to be back after only 1 absence, and, well, here it is, week 4. And, that's the military for you.
Yeah.
So, Nux, I almost didn't send you this email that we're having this class, because I figured you were gone goose.
I've been checking the notes
Yeah,
on the class, on Leo, so I saw how they were.
good.
I will pick up her.
You're a rare person if you can learn it from, just the Leo alone, so good for you.
I've been trying to, but it's hard.
Karen took your line, she said, I'm so glad you're teaching this class. So you can't say that now, she already said.
Oh, I can say it again. Thank you so much.
Good to see you, Nux.
Thanks,
I'm
sir.
glad your
Glad
foot
to be
turned out
here.
okay.
Trying to catch up right now.
Look at those boots, really.
That's gotta be an algebra class.
Beg pardon? That is an algebra class. It is an algebra class. 5th grade.
Right?
Nope, we teach that in here last night.
Is that
I
the one
used to
that-
love
It
those.
is, we do those rest. It's a very popular course, everyone takes it. Not, they would take it anyway, even if it wasn't required, I know, but we get full houses. I'll go, Sean. Good, thank you. So we're gonna have a good turnout.
Yeah.
Only 4 minutes to go. That's terrific. As long as your phone doesn't
Yeah, I'll-
turn on. Hello.
How are you?
Good to see you. You taking off
You.
a few minutes from work? Shh, no, secret, that didn't say. Okay. No, Ernie's not here. No, Ernie's not here. They're coming, Ernie.
So did you review the oral presentations?
No,
Not yet?
I knew I was forgetting to do something. I've been so busy with this missing lecture crisis. Definitely have to do that. Yep.
Do you have our grades?
For quiz 3? Not yet. Quiz 2 on.
Get the homework from, because we didn't get our homework back.
Not like that, I'm sitting right on it.
Oh, okay.
Yep. So 30 seconds. So I'd like to welcome everyone to our overflow auxiliary Stat 200 class. It has been clearly demonstrated to me that Stat 200 should not be taught in a once-a-week hybrid mode. It should have the traditional twice a week, so I've supplemented with this extra session. We'll meet every Tuesday for the remainder of the course. Attendance is optional, and I'll do a strict lecture. There won't be any whiteboards or that kind of stuff. Of course, I'll show examples upon request and that kind of stuff. But primarily, the weakness has been an understanding of the concepts and a knowing what to do, what the problems are actually asking for, and how to get started. So that's what we're going to try to improve in this. We'll start at 4:40, and we don't have a firm ending time. We have to clear the room by 7:20, but it's quite possible we'll stop quite a bit earlier if we get our task done. So it's interruptible, so ask questions, make smart butt remarks or anything like that anytime you feel like it. I do have to say that this is being videoed so that the students in Iwakuni can see the tape later tonight and not miss out on it. But I have to get your approval. So please throw a chair out the window if you don't want this video to take place. All in favor of video, raise right hand, or one of the hands, video is good to go. I do have to get your permission. And also, if you don't wear uniforms, then I can list the video as unlisted instead of private, which helps the distribution also. So it helps a little bit if you do civilian clothes. Not firm, but it's not a big deal if you don't. Now, this past weekend, I was down at a faculty workshop meeting, and one of the topics was discussion was these free textbooks. Everyone agrees the price is great, so they want to know about the quality. And all the other courses, like biology, writing, and psychology, said it was not possible to use the books. They were substandard. They weren't even usable. They were bargain basement. Yeah, I'm saying this on tape. And they got irate. One professor here refused to use them and said, send me a real textbook if you want me to teach. So the powers that be at Adelphi are aware of these criticisms, but they're committed to a full-speed approach that there will be no priced textbook by fall. Everything will be freebies. So they asked me, how about the Stat 200s? And I said, our Stat 200 freebies are adequate. They're no more than that, but they are adequate. And I say, part of the reason they're adequate is I spend 50% teaching on videotapes to supplement them. So I said that compared to the textbook that we used to pay for, which is this one, don't compare. This is a fantastic and excellent textbook. If we had this textbook, you could learn a lot more. And your pocket would be $180 lighter. So just as a show of hands, how many would opt to pay the $180 and get a fantastic textbook and double your learning?
Well, would the class still be set up like this with the textbook, or would it be in a different class setting?
Well, same setting. It would be the same setting, once or twice a week with the textbook.
Oh,
The only
okay.
difference is this textbook would replace the freebies that you downloaded. Okay, raise hands if this is what you like. Okay, I'm going to report that back, that I had 80%, 90% request that we go to $180 textbook and scrap the freebies. Maybe they'll see the sense. I don't know. And this is the best course. The other courses are worse.
Why don't they load that?
Load it, it's copyright.
No, sorry, I will.
Yeah, because of copyright. And the other thing is, it comes with adaptive learning. Like my math lab, you can go in and it'll lead you through problems. If you get stuck, it'll give you hints and give you similar problems of the same type until you can get through one. And that's a very strong feature. So I was all in favor of these freebies when I first saw the concept. I was a little less enthusiastic when I actually saw the printed pages, so what we were going to have to work with. And when I saw how poor they were at getting the ideas across to students just aren't learning from them, then I started reinventing the price textbook again. You get what you pay for. This may or may not work out, but by fall, all of the books will be freebies. And they say the quality will get better. And we have another course, Math 103, that also has an excellent textbook, which I told them it was excellent. So they asked me to find some freebies to replace it. So I've been tasked with that. So I got one foot in both camps now, so we'll see how it turns out. Okay, so what I'm going to do today is tackle this week's work, and I'm going to do it in an explanatory mode, and then we'll work through some sample problems. So before we get started, are there any questions about the material, about the structure, about what I'm planning to do, any of that stuff at all? Okay, now I'm going to start with an example, which is out of this $180 textbook, typical $180 quality, which Jakowski just skims over. Now I'll lead you through this, so don't try to lead it to get it all at once. And first, let me remind you of the terms population and sample. For example, all the people in Misawa Air Base can be defined as our total population, true? Now, If I say that it has 10,000 members, then I use a capital N to designate the number of members in a population. If I take the mean of the population, what symbol do I use? A mu, right. Okay, now if I don't do that, but I take a sample of 100, then I designate the number 100 with a small n, which means it's the size of a sample, small n as opposed to capital. And I designate the mean by not mu, but x bar. X bar, agree? Now, we go back to the population, I designate the standard deviation by the symbol
Sigma.
sigma. And if we come back to the sample, I designate the standard deviation by the symbol S. Okay. So those are just our symbols. So I'm going to start with this population, which is a fairly small population, and I designate its membership by capital X, and it comprised of the numbers 1, 2, and 5. So it's quite clear that n equals 3. This is my entire population, these three numbers. Now it's on a sheet in front of you, it's written at the top of the page. You don't like to write it down. So let's find out some properties of this population. First, no pencils. What's the mean? Mu. N, it's a fraction. 8/3, agree? Okay. Now, what I'm going to do is form some samples of size 2. I'm going to take samples of size 2 from this population. So you might say, well, that means you're going to take 1 and a 2, a 2 and a 5, and a 1 and a 5. But I'm going to take samples with replacement. In other words, I'm going to take a 1, then I'm going to put the 1 back. So I can pick it again for the second member. This is called sampling with replacement. And the reason we're doing it is because when you have a very large population, like 200 million, then the statistics are indifferent whether you put the person back before you pick the second person or not. Because if you put them back, then the odds of the second person is 1 over 200 million. If you don't put them back, the odds are 1 over 199,999,999 million, which is insignificant. So, and then you have independence of the two choices, which makes the arithmetic easier. So we always sample with replacement. It's a little strange in a small population like this, but in a large population, it's unnoticeable. So some samples that I could have are 1 and 1. Another sample is 1 and 2, or 1 and 5. Or I could have 2 and 1, 2 and 2, or 2 and 5. Or I could have 5 and 1, 5 and 2, or 5 and 5. So, how many samples did we create with replacement out of a population of 3? 9. And that's because we had a population of 3 and we took them 2 at a time. So it's very easy to figure out how many you'll have in any size population with any size sample. So the general is capital N to the small n power. And by the way, I put some videos of myself out there on Leo, and I really want you to look at them because they work through the same example that I'm working right now, and they will get the idea across. So I really do want you to look at the videos that I put out, that I made myself. But the editing is poor. I keep saying this is part 2, this is part 4. Ignore when it refers to some other part. That's not a big deal. So now I'm going to, for each one of these samples, I'm going to take a mean for that sample. So if your sample consists of 1 and 1, what's the mean? 1. This mean is 1.5, agree? And this mean is 3. This mean is 1.5 again, right? And this mean is 2. This mean is 3.5. And this mean is 3. This mean is 3.5. And this mean is 5. So you can do this with a whole population. If we took the 10,000 population of Misawa Air Base and we broke it into samples of 100, then how many samples could we find for a complete set of samples? It would be 1,000 to the 100th power, which is 100,000. So you get 100,000 samples on the solid air base of size 100 if you have a population of 1,000. That 100,000 set of samples is called the complete set of samples, because it's every possible sample that you could have made in the population for that sample size. And that's called a complete set of samples. Do I have a complete set of samples here for this population? Yes, I do. Now I'm going to show you a very interesting fact. Here I have a list of the mean values. Now, this is also a population, even though they're samples, because this is a complete set of the means, is it not? This is the complete set of the means. So I can take a mean of the means. Are you ready for that? What's the average value of the means? These are all means themselves. Each one is a mean of a sample. But once I formed a new data set, here I have a new data set, and any data set can be averaged. You can find the mean of any data set. This happens to be a data set of means. But I can find the mean of that, can't I? So when I find the mean of that, I'm finding the mean of the means. And this is what's known as the sampling distribution. The mean of the means. If you take a complete set of samples from the population, and you take the mean value in each sample, and then you take the average of all of those mean values, then that's the average mean, the mean of the means. So it's the mean of the means. It's the mean of the means, and the notation is mu x bar. Now I'm going to show you an amazing fact. What was the mean of the population? Now I want you to find for me, what is the mean of the means? Add them up and divide by 9. Add them up and divide by 9. And you get? 8/3. This is the most amazing and profound result in all of statistics, if not in all of mathematics. That the mean of a complete set of sample means is the same as the population mean in all cases. The mean of a complete set of sample means is the same as the mean of the population. And it can be algebraically shown to be true. So I did algebraically show it to be true in those 7 videos that I put out there for you to watch. You don't have to understand the algebra, but it just might be satisfying to know it can be algebraically proven, and it's not that difficult. So for any population, no matter what the population, if you form samples of a certain size, and you make sure you get every possible sample of that size, that's called a complete set of samples. Each one of those samples will have a mean. And if you take the mean of those means, then you've got the sample mean, the mean of the samples. And that mean of the samples will algebraically always be the same as the mean of the population. So that means that the mean of the sample means targets the population. It targets the population. Now, there are some other properties that you can compare. First, I want to talk about the shape of this distribution. The shape of this distribution is very interesting. Is this a normal distribution? If I graphed it. If you graphed it, it would have a 1, a 2, and a 5. Does that look like a bell-shaped curve?
No.
This is not a normal distribution, agreed? And it only has a size 3. But the amazing fact is that as long as the size of the population is sufficiently large, like say 30 or better, no matter what the shape of the population distribution, the shape of the sample means will always be a normal distribution. Now let's prove that to you with this handout. Also out of the same $180 book. Now, in the column on the left, the population called n equals 1. That means that the population is the sample, agreed? So at the top left, the graph, is the graph of the population. And is it not a normal distribution? You can draw a bell right around it. Now what we've done is create, in the middle graph, all possible samples of size 10. That's a complete set of samples of size 10, okay? And for each one of those samples, we calculated the mean value. And then we plotted those mean values. So the middle graph is a graph of the sample means. It's called the sampling distribution. Now, even for samples of size 10, do you not notice the bell-shaped curve forming? And now the graph at the bottom, if you go to a larger sample size, then you get an even stronger bell-shaped curve, agreed? So you see how these sampling distributions assume a bell-shaped normal distribution, which means that you can use your z-tables on it. Because your z-tables are restricted to normal distributions. Now let's go to the middle graph. What is the actual distribution in the population? Is it bell-shaped? No, it's flat, it's uniform, agreed? Every number has equal representation. But the amazing thing is, if you take all possible samples of size 10, and you take the mean of each one of those samples, and you make a plot of each one of those means, then do you get the bell-shaped curve emerging? And notice, is not the center of the bell-shaped curve the same as the center of the population? The mean of the means is also the mean of the population, true? Now you go down to the bottom graph, and you go to size 50, and now you get a very strong and clear bell-shaped distribution, agreed? And again, is not the mean of the means exactly the same location as the mean of the population? Dead center. Mu equals mu x bar. Now, let's go to the worst shape at all. The U shape on the right. That's an inverted bell-shaped, isn't it? You can't look at any distribution that is worse bell-shaped than that one, is it? It doesn't go up in the middle, it goes down in the middle, true? Worst possible case. But, once again, if you take the sampling distribution, does it become normal? It becomes normal. So this is amazing, that no matter what the shape of the original distribution, the sampling distribution, that is the plot of the means of all of a complete set of samples, will be bell-shaped. This is known as the central limit theorem. One of the main things you had to learn for this week. So the central limit theorem is, irregardless of the shape of the population distribution, the distribution of sample means will be normal. And the mean of the distribution of sample means will be the same as the mean of the population. And that's our fundamental lesson for this week. Now, as you observe, we're dealing with two graphs. First here, we have the graph of the population. And I'm going to assume it's bell-shaped, just for simplicity. It has a size n, true? And it also has a mean mu. Now I'm going to break it into samples of size n. And I'm going to break it into a complete set of samples of size n. And for each one of those samples, here I'm plotting x, some parameter. Now in my second graph, for each one of those samples, I'm going to find its mean. And now instead of plotting x, I'm going to plot the mean of each sample. The mean of each sample. And I'm going to have a lot of samples. In fact, I'm going to have n to the n power number of samples. So I'm going to have a lot of dots here. So when I put the dots here, then it will also be a bell-shaped curve. And it will have a mean mu of x. And mean mu of x bar is going to be equal to the mean of the population. They will have the same numerical value. The other thing I want to remind you of is the standard deviation. If here, the standard deviation is known and it's equal to sigma, then here, the standard deviation will be sigma over the square root of small n, the sample size. So even though this is bell-shaped and has the same mean, it does not have the same standard deviation. Now, is this standard deviation smaller or larger than that one? It's smaller, isn't it? And you can tell that because it's skinnier. So the sample distribution will be thinner or skinnier than the original. And this enabled us to answer one question in lane number 16. So everyone read question 16 in lane, page 327. So Ernie, could you read it aloud to us, please? Question 16 in lane on page 327. You got it there? Okay, volunteer,
Okay.
go.
And the population, the mean SAT score is 1,000.
Okay, let me name that down. So what we're talking about here, this is mu equals 1,000. Mean SAT score. Does that mean this number is also 1,000?
Yes.
Okay. Now, continue.
Would you be more likely or equally likely to get a sample mean of 1,200 if you randomly sample 10 students or if you randomly sample 30 students?
Okay, now, here is the value 1,200. Okay? Now, what is the standard deviation here if I have 10 students? It's whatever sigma was over there, sigma over the square root of 10, agreed? Now, let's take another case which involves 30 students. Now, if n is going to be 30 instead of 10, I'm going to get a new sampling distribution. Is my new sampling distribution going to be skinnier or fatter than the one with 10? That's right, skinnier. Because this standard deviation is going to be the same sigma over the square root of 30. So which is smaller? Sigma over the square root of 30 or sigma over the square root of 10? Which is smaller?
Square root of 30.
This is smaller. So that means that it's, here we have one standard deviation, two standard deviations, one standard deviation, two standard deviations for our usual 68%, 95% degree. So up here we have one standard deviation. So now here we have the value 1,200. Now, which is going to have more students? This one or this one? Top one's going to have more students because this is fewer standard deviations away. So this is one of the hardest problems in lane for today. So that means that if this is broad curve, then numbers will have fewer standard deviations. They'll be closer to the 68%. But if the curve is very sharp and narrow, then the numbers are way out in the tail. They're in the 99% location. So they don't have much representation. So that's comparing two values of n to each other in question 16 is what we did there. So you can think about that a little bit. Now, let's return to our situation here and going to ask for some other statistics or parameters. For example, the next one that they're interested in this table, and you can take your table out again, is the variance. Now the variance is a standard deviation squared, agreed? We don't use it so much, but that's what it is. You know what the standard deviation is? Well, the standard deviation squared is called the variance. So let's calculate next the variance for each one of our samples, okay? And it's done here in the page. And then if you add them up, then you're going to get 26 over 9. Now the formula for the variance, for those of you that have not remembered it, it's a summation of x minus x bar quantity over n minus 1. And if you want the standard deviation, you take the square root. So what they've done for you is do the calculations, not make it hard for you to do. So you find the formula called variance. Okay? You see the variance for each sample. So, Sean, can you read the list of variances?
We got 0.0, 0.5,
Hmm.
8.0,
Right,
0.5,
right,
0.0,
Right.
4.5,
right.
8.0,
Right.
4.5, 0.0.
Okay, now if you averaged up those variances, you would have the mean variance of the samples. And they did that, and what did they get for the mean of all of these sample variances? What did it come out to be?
2609.
Good. Now, they went back to the original population. The original population was 1, 2, and 5. And you can calculate the variance for that using the same formula. And they did that. And what did they find for the variance of the population? 26/9? Everybody find it? Dawn, you find it okay? So, now, is it also true then that the variance of the sampling distribution targets the variance of the population? It's also true that they turn out to be the same. Now let's look at the standard deviation. What is the mean standard deviation for the complete set of samples? 1.3. What's the standard deviation of the sample, of the population? So does that target it? No, it doesn't target it. The next one is proportions. Now, they're illustrating proportions by looking at the proportion of odd numbers. In the first sample, which is 1, it's got 100% proportion. Agreed the proportion is 1. They're both odd. The next one, 1 out of 2, 0.5. So you add those up in average, then the mean proportion of odd numbers in all of these samples is 2/3. Now, if you look at the board, 1, 2, and 5, what's the proportion of odd numbers? 2/3. So the proportion is also targeted. Those are the only three statistics that transfer from the sampling distribution to the population. The mean, the variance, and the proportion. All of the others, like median, does not transfer. Mid-range, they do range here, they show you that doesn't transfer. And standard deviation does not transfer. So this is a great page. And down at the bottom, you see the bold print. So Dawn, could you read to us statistics that target population?
The statistics that target population parameters, mean, variance, proportion.
And the next.
Statistics that do not target population parameters, median, range, and standard deviation.
So now we understand what it means to target the population parameter. It means that if you form a graph, as we've done, of a complete set of samples of that size, and you take either the mean, the variance, or the proportion for that complete set, then the middle point of that will be the same as the middle point of the same parameter in the population. Identically the same. And that's called the central limit theorem and sampling distribution. And it's very, very powerful. Now, let's go to this next page again, because it's going to be what you're going to be doing for the entire set of problems. In the original population, the mean is mu. The standard deviation is sigma. It's a normal graph. Let's say it is. It doesn't have to be. But if it is a normal distribution, it'll look like that. It will have a companion graph. A graph that is made from the first graph by the following process. You select a sample size n. In the original population of size capital N, you generate all possible samples of this size. You look at each one of those samples and you find its mean. And that's a data point for your second graph. And then if you shape these data points, you will find that they're also a normal distribution. And what will you find about the center point of this second derived graph? Same as the center point of the population. But its standard deviation is not the same. The standard deviation is sigma over the square root of n. Here the standard deviation is sigma. So in the sampling distribution, what's the formula for the standard deviation? And it's called the standard deviation of the sample means. This is the notation, is equal to the standard deviation of the population over the square root of n. So this is the standard deviation of population, this is the standard deviation of the second graph, the distribution of sample means. It has a different notation. So this is sigma x bar, this is just plain sigma. And they're related, that sigma sub x bar is sigma over the square root of n. So now we can do some problems in length. Number one. So we're doing lane number one. A population has a mean mu equals 50. Okay? And sigma is equal to 6. So A, if you have I don't like what Lane's doing. He's using capital N instead of small n for the size of a sample. So just work with him. That's abnormal notation, but that's okay. Suppose you have the size of the sample is equal to 16. What's the equation for the standard deviation of the sampling distribution? Sigma sub x bar equals what? Sigma over the square root of n, agreed? Now, you're given sigma, you're given n, just plug it in. And see what you get.
0.5.
All right, one more time. Thank you. Don, do you see why it's 1.5? Okay, let's put in the numbers right here. Watch. What's sigma? 6 over the square root of
16.
equals 6 over 4 equals 1.5.
Is that what you were saying? That, oh, like, I guess that threw me off earlier. It's, I ain't using that big N, but it should be a little N, right?
Let him know. Let him know. It's a non-standard notation. But it's very clear because he says it in words. That n is equal to 16. The sampling distribution of the mean for n equals 16. Okay, so we're correcting that typo in this part. Now everybody do part B. I'm not going to do it to see if you get the same answers as each other.
I don't have a copy of it. So, I don't have a.
Well, is there some kind classmate that Karen can sit next to? Sean? And, yeah, you want to come over there? Yeah, we got to bring these questions to class.
So the mu in that problem had nothing to do with actually speaking.
Has nothing to do with actually speaking. That's right.
Sorry, I was trying to use everything.
That's right. No, no, you have to understand. You have to understand, not go to jail for Okay, so what did people get for part B? Nux, what did you get for part B? You don't have the paper.
No, I got the paper here, just did.
You got a calculator.
Yeah. Okay.
No calculator. What are the numbers? How should you do the numbers? Sigma x bar equals what? Sigma over the square root of n, true?
Yeah.
What's sigma for this problem?
See this, 6.
6. And what's n for the part B?
1.
Okay, so there's the numbers. So this is called the standard deviation of the sampling distribution. Now, it's in effect whenever you are working with the sampling distribution. If you're working with the population distribution, then this is in effect. If you're working with the sample distribution, then this is in effect. So we have two distributions. Yes, sir.
Because you said, the standard deviation usually changes when you need to put one, but that, the second part B, I thought since we have six, since we have six for the first,
Yeah,
for the first, sigma, I thought it was changed, it would change in the second problem, or same to the same six.
it changes from, no, it doesn't change, because all we changed in the second problem was n, and we're still working on the same population. So it's the same population, therefore sigma does not change, because the population did not change. Okay, is everybody on solid ground on that one? Okay, now let's go to number 2. Now remember, this very clearly illustrates that we're going to have two graphs.
Yeah, if you unlock it and you turn it to the side, there's a square root, it says 2 over the square root of x,
I don't have this, but I think it's six on it.
and then it's there.
Thank you.
Yeah.
Okay, now in problem 2, we have a population that is normally distributed, and it has a mean of what value? 100. And it has a sigma of what
12.
number?
Oh,
12. Now, from that, we generate all possible samples, and for each sample, we take the mean. So we generate the sampling distribution, which is going to be thinner. And it's going to have a mean of what?
100.
That's not going to change. But it's going to have a sigma x bar equals sigma over square root of n, true?
Yes.
Okay, so now, let's go. A, the probability that a single score at random will be greater than 110. Now, I want to ask you, are we talking about a single individual here or a single sample? If we're talking about a single individual, we use this graph. If we're talking about a sample, we use this graph.
Single individual.
This is a single individual, true?
Mm-hmm.
So we use this graph. So what we want to do is put in our z-axis, and here we have 110. And what we want to know is that the probability will be greater than 110. So what we want is this shaded area. So use the formula for z. What's the formula for z? Z equals
X minus x bar.
x minus mu. This is population.
Mu divided by sigma.
That's right. So what is the x that we're dealing with? It's 110, mu is 100, and what is sigma for the population? 12. So find the z value. What do you find?
0.83.
0.83. So now, you take your table. So Karen, are you adept at using your table now?
Oh, yeah.
I was a little bothered by people that hadn't had their tables printed out because they weren't reading the news. So now in your table, find a z value of 0.83. Nux, you got table. Okay. Ernie, can Nux, I don't have an extra table.
You can use mine, I have it on my phone
Okay.
too.
Yeah. Okay, so this is just like Math 103. So now find 0.83. So find 0.8, go to the third column. I got my number. What is it, Ernie? What you get for that 0.83?
0.7967.
Right, so P equals, 0.7967. Now, have I found the red that I'm looking for, or have I found the green, which I'm not looking for?
The green.
The green.
Found the green. So how do I transform that to the red?
Subtract.
Minus that, which would be 2033, right?
Mhm.
So P equals 2033. Why minus that? Because we're working to the right, table gets to the left. So that's part A. Now, part B, the probability that a sample of 25 scores will have a mean greater than 105. Am I going to use the graph on the left or the graph on the right?
Right.
I'm talking about a mean, right? I'm going to pick one mean at random from the complete set of means, okay? I'm going to take a random sample. If I take a random sample, then this is the graph that describes the samples. So this is the graph that we use. And now we find the z-score here using this graph. Z equals. Now, what we have is an x bar, a certain x bar minus mu of x bar over sigma of x bar. Now, notice that this sigma of x bar can be written as what? Sigma of x bar is equal to what? Sigma over?
Square root
Square
of
root
n.
of n.
So I can make that substitution, sigma of the population over the square root of n. So notice, if you're dealing with the population, this is a sigma. If you're dealing with the distribution of samples, this is sigma over the square root of n. So now put in the numbers. What is the particular sample mean that they're talking about? In B. What is the sample mean that they're focusing on? 105, right? Karen, you see it's 105? So this is going to be equal to 105. Now, what is the mean of sample means?
The same,
And that number is
100.
100. Now, what is sigma? It's 12. And what did they tell you that the sample size is? Square root of 25. So now do the arithmetic and tell me what the z-score is. And Kayla, what is the z-score?
2.08.
2.08. So now you have to go to your table and convert that to a probability. And what does it come out to be?
0.9812, sorry.
0.9812. Now, is that the one that you're looking for, or are you looking for this one? Which is it that you're looking for? Are you looking for the green or the red?
The red.
Looking for the red, because they want the probability that it will have a mean greater than 105, agreed? So that goes in the direction of greater numbers, to the right. Now notice that what we have done is we have taken one sample at random, and we want to know the probability that the mean of the sample at random that we chose will be greater than 105. So each sample will have its mean, and if we choose a sample at random, it could have any mean at all. But there's a distribution of sample means. And we can use that distribution with the z-scores, because it's always normal shaped, to find out the probability that the sample we picked will be greater or less. So now C, you do C, and I'll just wait your answer. So what did anybody get for an answer for C, except Taylor? What did anybody get for the answer for C?
Nothing yet.
You do it just like the B that I did, only you use 60.
3.3.
3.3? Well, Taylor's agreeing, that makes it authentic. Now, D is going to slow you down a little. Yes, sir, ma'am.
It's 3.33, that's the z-score you get. You have to figure out what the probability.
That's the z-score. Okay, now take the z-score into a probability. And so, draw and finish off the problem.
0.9995.
Okay, now, is that the number that you want, or do you have to subtract that from 1? Dawn, which one? You want to go greater?
Greater than, so it's the number I want.
No, because the table gives you the sides to the left. Table works to the left. Karen, you okay that the table works to the left?
Mm-hmm.
And you have to, these problems go to the right. Now, the next one's very right. Now, the next one's very complicated. It's got little steps to it. Less than 95 or greater than 105. So I'm not gonna do that on the board, because we're gonna leave something to do Thursday on the whiteboards. So when you come in Thursday, I want all of you to be able to put that one up on the whiteboards. 2D. And if you get stuck, you might email your classmates and work as a group, or something like that. Statistics cannot be taught hybrid.
Can I ask a question?
Yes, ma'am,
Okay, on C,
on C.
because we're looking for the right again.
Yes.
The calculator will not subtract 9996 from 1.
Yeah, it gives me like negative E.
Yeah,
Yeah, that's right.
it's coming up with
Well,
an
then
error.
just do it on paper.
Okay, so it's
Be like
0004.
0004.
The old-fashioned way.
Okay. I just want to make sure.
Yeah. And spend more than $1.50 for your next calculator.
Oh, wait a minute, I spent 50 bucks.
And it won't do that. Well, it goes into scientific notation, that's okay. Once it gets more than 2 decimal places, it goes to scientific notation, that's
Right.
good. Okay, now, number 3 is a literature search. You have to read Lane's pages. I'll leave you to do that as well. And 4, now, the standard area of the mean, what do we mean by the standard area of the mean? What's that term mean, standard area of the mean?
Oh, standard error.
Well, you gotta look it up in the text. That one you should have been able to look up. First, what's the answer to number 3? What term refers to the standard deviation of a sampling distribution? You gotta find that in the text. Not on class time, that's your own time. What term refers to the standard deviation of a sampling distribution?
Line over X.
It might be on Ilkowski's formula reviews and definitions. Let's see what she says. For her key terms, it just might be there. Yes, it's on her key terms. If you look at Ilkowski, page 395. Standard error of the mean is the standard deviation of the distribution of sample means, or sigma over the square root of n. We've been calling it the standard distribution of sample means, agreed? And now she's telling you, everybody is telling you, that it has a second name. And the second name is what?
Standard error.
Standard error of the mean.
Right.
So it's just a synonym.
So, what?
Yeah, it's sigma over the square root of n.
Yeah.
Standard error of the mean. Now, so in 4, so what's the formula for standard error of the mean? Mean is sigma over the square root of n. Or is it a standard deviation of sampling distribution, or the standard error of the mean, as your mood suits. Call it what you want. Now in this problem 4, they tell you that if n equals 12, then sigma sub x bar, which is equal to the, sigma over the square root of n, becomes 10 equals sigma over the square root of 12. And then they ask you, question, if n equals 22, then sigma sub x bar equals what? So you use the given information to find the asked for information. And awful news, you have to think about it a little bit and play with it. But if you think about it and play with it, then you can get the answer. And part B is a repetition of the same strategy that you developed for part A. This is not a simple course. It's a course that has a reputation for being the hardest course in your required courses, and it deserves its reputation. You actually have to think in this course. And even if thinking, some of the problems you won't get. It's a hard course. So be prepared to stare at the wall and cogitate. It's not going to be plug in and grind. It's going to be understanding. So that's the type of course it is, a concept course. Okay. Now we go to number 7. So Sean, could you read 7 to us, please?
If numerous samples of n equals 15 are taken from a uniform distribution and a relative frequency distribution of the means is drawn, what would be the shape of the frequency distribution?
And your answer is? What you're doing is drawing a sampling distribution, aren't you?
Yes.
And what's the shape of all sampling distributions?
Yeah, normal
Normal,
distribution.
done. Next question. Normal, bell shape. Because it's a sampling distribution. They call it a frequency distribution, but a frequency distribution is what it actually is. It's a distribution. So bell shape. Now, number 10 is a thought question. So I want Dawn to lead the way. If you sample one number from a standard normal distribution, what is the probability that it will be 0.5? Okay, let me make the question a little bit clearer. If in this class I pick one person's height, what's the probability that I will pick a person with a height 6'2", 7', 8'1", 9, 6'4", 2, 0, 0, 12 inches tall? What's the probability I'm going to find someone with that height? 0, right? And that's true for these bell-shaped curves. The probability of any single value is 0. So you can only use these bell-shaped curves for probability intervals. The probability between any two numbers. The probability of any single number is 0 because it's an exact value, and the chances are that nobody in the population is going to have exactly that value. So the only thing you can use these bell-shaped curves for are for intervals, not exact values. So 14 we're skipping, so we go up to 16. And we did 16 already. 17, 19, 20, and 21. And I'm going to leave those for your work. We've told you the material that you need to do them. So you've got 2 days, should be able to crank through them. Okay. Good. Now when you come in, I really want you to be able to put these in the whiteboards and discuss them with your mate classes so that everyone can educate everyone. Now let's go to Ilkowski. And I think I indicated there were two key terms that will be on your test. No maybes, ifs about it. Does anyone recall what those two key terms were?
Sampling distribution and standard error mean.
Okay, who can recite them from memory already? Get those points.
Standard error.
Of the mean.
It's a standard deviation of the sample means.
Good. And you memorize those, pick up a few points. No thought involved. Okay, so let's go to her problems, like number 1.
So what page is that?
Problem is on page 396, same as my age. If you look at her formula review, which will be in front of you on the test, then you see that the z-value that you're looking for is given to you there, and also her notation. The central limit theorem for sample means. X bar is described as a normal distribution with a mu of mu x and a standard deviation of sigma x over square root of n. So this is formula review, the first formula review. So Sean, do you understand that first item in the formula review?
The X bar, you mean, the
Yes,
central
X-
limit theorem?
Okay, if I write this on the board, what am I saying? X is equal to n 5, comma 2. What am I describing? First, what does the n stand for? So just show us. No, n stands for a normal curve in this notation. This means it's a normal curve, a bell-shaped curve. What does the 5 stand for?
That's the median.
The mean.
Mean, right.
And what's the 2 stand for?
Standard deviation.
Standard deviation. Now, is this a population graph or is it a sampling distribution graph? Hence, this is what it could be. X bar is equal to a normal distribution of 5, comma 0.4. What is this saying? What's the n stand for?
Sampling size.
Bell-shaped curve, right? Normal distribution. Where's the mean of this normal distribution? And what's the standard deviation? And what is it that I'm distributing? Means, right? So which one of these is a distribution of sample means?
The one on the right.
This one is a, which one? This one is a population distribution, right?
Right.
Because it just has the raw data, X. Okay, now number 1. Complete the distributions. What is the mean, standard deviation, and sample size? So you read the information and you pick out these numbers. So go ahead and read and pick out. Ernie, this is really hard in your second language. It's hard enough in your first language. So I sympathize.
So page 396 or something?
Sir?
What's the page you're talking about?
396?
396.
Yeah. Now, I can't work from an e-book. I've got it printed on paper, so do what you do.
I'll try to print it out.
Yeah, it's only about $20 printed out, but do what you do.
Claire and I had an argument.
Yeah.
Yeah, it's like $29 more per hour.
About
Well,
20.
I have to do.
Okay, let's
I
continue.
have to do.
What is the mean of this information?
Number that measure the central tendency.
Right, in other words, what
average.
is the mean time? Now, X, what does X stand for? Let X be what? Random variable representing the
Time it takes.
time for one review, agreed?
Yeah.
Now read in the information, how long does it take her to do one view
4 hours.
on the average? 4 hours. You put the n there, right? Then after you put the n, you put a 4. And then you put a comma, and what's her standard deviation?
1.2 hours.
1.2. Now, okay, we're doing number 2. Now 2b, what do you put? You put the n there, don't you?
Yes.
Now, what's the mean of the sample distribution?
4.
4, unchanged, true?
Right.
But the standard deviation is changed,
It's 1.2 over the square root of 16.
which is 4. So final answer, 0.3. Now let's go back to 1. What's the mean?
4 hours.
What's the standard deviation?
1.2.
Okay. Now, what's the sample size?
16.
Good. Now here's a question for me. What's the median of the population distribution? What's the median?
16.
Wow. 4.
Kayla knows it's 4. Why is it 4? It says assume X is normally distributed, right?
Right. So
If you have a bell-shaped curve, what 3 averages are at the same place?
mean,
So what's the median of the sampling distribution?
One.
Those questions occur later. So now find the probability that one review will take Yoni, from 3.5 to 4.5. Which curve are you gonna use? The population curve or the sampling distribution curve? Population curve. Okay, let's go to next question. Oh, now they even give you graphs here that they want you to fill out on, but you don't have to. And then they give you the same notation, P, you fill in the numbers, okay? Now 5, and then for part 4, so Sean, you read, Dawn, you read 4. Find the probability that the mean of a month's review, now which distribution you take, population or sampling distribution? Sampling distribution. It will have a different standard deviation, true? So then you go to your z-table, and you can use the z-table because it's normally distributed. Yes?
It says find the probability of a month's review, so do you want us to do 30 days?
Well,
Oh, a month, oh, 16.
Okay.
Yeah.
I was really getting disappointed in you for a
Awesome.
moment. Right, not a month, but a month's reviews, got it.
That's
Now, 5, anybody, what causes the probabilities in these two examples to be different when they had the same hour rates from 3.5 to 4.25? What's the probabilities different? So, Karen,
Because, they're two different distributions.
what about the distributions is
Well,
different?
one is population and the other is, sampling distribution.
Yeah, we know that, but that's in the question. We need the answer.
Yeah,
What's different about the two curves?
because you're using the standard deviation.
Exactly, they have different standard deviations, agreed?
Right.
It's because they have different standard deviations, which is the only thing different about them, is the reason the results are different. Okay? Now, I'm getting a little afraid we're doing too much of your homework for you, so we're going to have to just pick and choose a few more. Let's go to 62.
Okay.
62. Okay, so Sean only, 62A, are you gonna use the population distribution or the sampling mean distribution? For A,
You're gonna use the
sampling, right, okay. Now, do you know how to handle a question like C? Find the 80th percentile.
I don't.
The 80th percentile means that this distance is greater than 80% of the possible distances, agreed?
Right.
So isn't that a probability of 80?
Yeah.
So where in the table do you look up the probability? In the body or in the side column?
That would be in the body.
You start with the body of 0.8, agreed? And that gives you a z-score, so you work backwards. So a percentile is a probability. And you take the percentile into the body of the table, and then you pick off the z-score, and you answer the problem. So let's, everybody, do C. Everybody do C. Find the 80th percentile of the distribution of the average of 49 fly balls. So a picture doesn't hurt. So this is 62C. So it is a normal distribution, and it's a sampling distribution. So sigma sampling is equal to 250 is equal to sigma over the square root of n, which is 50 over the square root of 49. And mu is equal to 250. So this is z equals 0. And now, we want the 80th percentile, so this is going to be 80%. 80%. So Z equals what for 80%?
0.84.
Equals 0.84, agreed? But Z is equal to X bar minus mu sub X bar over sigma sub X bar. Now, this problem works backwards, because you know Z now, 0.84, X bar is what you're looking for, mu sub X bar is 250, and this is 50 over the square root of 49. So solve for X. Solve for X bar. So this is a backwards problem. They give you the information to find Z, and then you use the formula for Z backwards. And find the data value. In this case, the data value is a mean.